In our today's lesson, we are going to derive the shear stress equation for an I-beam section. Now, the figure above shows an I-beam section with a depth of D, capital D, and a breadth of capital B. The depth of the web is small d. From the neutral axis to the upper edge of the flange, we have d over 2. That is half the depth, because the neutral axis is cutting this I section into two equal parts. From the neutral axis to the lower edge of the top flange, we have small d over 2, which is equivalent to y. Bar y is the distance from the neutral axis to the center of gravity of the top flange. Remember, this I-beam section consists of three components. We have the top flange, we have the web, and we have the bottom flange. Now, for us to be able to derive the shear stress equation for this I-beam section, we are going to consider the shear stress equation that we had derived in our previous lesson. So, if you are yet to watch that derivation, please consider doing so and subscribe to our channel, give us a thumbs up and comment. Now, shear stress is given by shear force multiplied by cross-sectional area times bar y. That is the distance from the center of gravity, from the neutral axis to the center of gravity of a section or a component. Divide this by the moment of inertia multiplied by the breadth. Now, first of all, we are going to determine the value of A times bar y. Now, starting with the area of the top flange, we are going to have the following. The area of the top flange will be given by breadth times its depth. Now, the depth of this top flange will be d over 2, that is half the depth of the I section, minus y. So that's going to give us the depth of the top flange. So b multiplied by d over 2 minus y. For bar y, the value of bar y, that is the distance from the neutral axis to the center of gravity of the top flange, will be given by y plus the distance from the lower edge of the top flange all the way to the center of gravity of the top flange, which in this case, the distance from the lower edge of the top flange to its center of gravity will be given by half its depth, and its depth is d over 2 minus y. Therefore, we are going to have y plus half the depth of the top flange, which will be a half into d over 2 minus y. So, solving for the bar y, we are going to have y plus, opening the brackets, d over 4 minus y over 2, which is going to give us d over 4 plus y minus y over 2. So this will result to, that is d over 4, now d over 2. So this is going to be bar y is equals d over 4 plus y minus y over 2, that is y over 2. Now, when we factorize, we are going to have a half into d over 2 plus y. So that is the value of bar y. Now, combining the two together or multiplying A times bar Y. Therefore, A times bar Y. This is going to be A, which is B, into D over 2 minus Y multiplied by bar Y, which is a half into D over 2 plus Y. So this is going to be B times a half, that is B over 2 into D over 2 minus Y, D over 2 plus Y, that's going to be D squared over 4 minus Y squared. Since A plus B, A minus B from the quadratic expressions and equations usually results to A squared minus B squared. So that is the value of A bar Y. Now, back to our shear stress equation. Shear stress equation is given by S A bar Y L over I B. A bar Y, we got it here. So we are going to have shear stress will be equal to S divided by IB multiplied by A bar Y, which is B over 2 into D squared over 4 minus Y squared. This B and this one are going to cancel out, and we are going to have shear stress being equal to S divided by 2 times I, which is 2I into D squared over 4 minus Y squared. So you have D squared divided by 4 minus Y squared. So you can call that equation 1. Now, on the top flange, we have the top edge of the flange and we have the lower edge of the flange. The top edge of the flange have got a value of Y being equal to D over 2. That is the distance from the neutral axis to the upper edge of the top flange. And therefore, considering the upper edge of the top flange, whereby the value of Y is equal to D over 2. From the neutral axis to the upper edge of the top flange, Y is D over 2. Therefore, substituting this Y at equation 1, we are going to have shear stress being equal to S over 2I into D squared divided by 4 minus Y squared. And Y squared is D over 2. Therefore, substituting D over 2 here, we are going to have D squared divided by 4, because D over 2 squared is D squared divided by 4. Now D squared divided by 4 minus D squared divided by 4, that is 0, making the whole of that equation to be 0. Therefore, the shear stress at the upper edge of the top flange is going to be 0. What about the shear stress at the lower edge of the top flange. So we go to lower edge of the top flange. Considering the same equation, y is d over 2. That is, the distance from the neutral axis to the lower edge of the top flange is d over 2. Y is equals d over 2. Substituting d over 2 at this point of equation 1, this is going to give us shear stress will be equal to S divided by 2I into d squared divided by 4 minus y squared, and y is d over 2, therefore d over 2 squared, that's going to be d squared divided by 4. Therefore, this is the shear stress at the lower edge, this edge here of this top flange. Shear stress distribution in the web. Now, consider a web section that is at a distance y from the neutral axis. This shaded web section, whose distance from the neutral axis is y. The center of gravity, that is the center of gravity of this shaded web section to the neutral axis, is bar y. Now, for us to get the shear stress distribution in the web, we are going to add the moment of the flange area about the neutral axis plus the moment of the shaded web area about the neutral axis, because the flange is lying above the web, and therefore it is going to subject the web into a shearing stress. That is the reason as to why we have to add the moment of the flange area about the neutral axis plus the moment of the shaded web area about the neutral axis. And that means that we are going to have a bar y for the flange plus a bar y for the shaded web section. Now, starting with the a bar y for the flange, starting with the area. The area of the flange in this case will be given by breadth times its depth, whereby the breadth of the flange is b and its depth is going to be d over 2 minus d over 2. That is d over 2 minus d over 2, we get the depth of the flange. Bar y for the flange. Bar y for the flange will be the distance from the neutral axis to the center of gravity of the web, which in this case we are going to have d over 2 plus half the depth of the flange. So this is going to be d over 2 plus half the depth of the flange, and the depth of the flange is d over 2 minus d over 2. Solving for bar y will lead us to d over 2 plus, opening the brackets, that's going to be d over 4 minus d over 4. This will result to d over 4 plus d over 2 minus d over 4, which will finally be d over 4 plus d over 4. That is, d over 2 minus d over 4 is d over 2, d over 4. Factorizing we are going to have a half into d over 2 plus d over 2. Now, multiplying a times bar y for the flange, we are going to have a, which is therefore a bar y, that's going to be area, which is b into d over 2 minus d over 2. Multiply this by a half of d over 2 plus d over 2, which will result to b times a half, that is b over 2 into d over 2 minus d over 2, d over 2 plus d over 2, that's going to be d squared divided by 4 minus d squared divided by 4. So that is a bar y for the fringe. Then you go to a bar y for the web. So the shaded web section, its area will be given by breadth times the depth, and the depth of this web is going to be d over 2 minus y. D over 2 minus y. Therefore, the area of the web will be its breadth times its depth, which is d over 2 minus y. Bar y for the web, that is the distance from the neutral axis to the center of gravity of the shaded web region. That is going to be y plus half the depth of this shaded web section. So that's going to be y plus a half of the depth of the shaded web section, which is d over 2 minus y. Therefore, bar y will be equal to y plus, opening the brackets at this point, we are going to have d over 4 minus y over 2. Good. We are going to have bar y is now going to be d over 4, d over 4 plus y over 2, because y minus y over 2 is y over 2. Factorizing this, we are going to have a half into d over 2 plus y. So that is bar y for the shaded web region. Multiplying the two, that is a times bar y for the web, we are going to have a bar y being equal to, the area of the web is b into d over 2 minus y, and bar y is a half into d over 2 plus y. Therefore, a bar y for the web is going to be b times a half, which is b over 2 into d over 2 minus y, d over 2 plus y, that's going to be d squared divided by 4 minus y squared. Therefore, that is a bar y for the web section. Now, adding the two for the fringe plus that one of the web, a bar y for the fringe is, so we are going to have b over 2 into d squared divided by 4 minus d squared divided by 4 plus b over 2 into d squared over 4 minus y squared. So from the shear stress equation, that is shear stress is equal to S A bar Y divided by IB. We are going to have shear stress is equal to S over IB times A by Y is, we got it there, B over 2 into d squared over 4 minus d squared over 4 that's 0 plus b over 2 into d squared divided by 4 minus y squared. But at the neutral axis, y is 0. The value of y is 0 at the neutral axis, and that's where the shear stress is maximum. So when y is 0, shear stress is maximum. So you can say that at the neutral axis, y is equals to 0 and shear stress is equal to maximum. Therefore, substituting this 0 at this point where we have y squared will give us S divided by IB into, when we factorize 4 out, we are going to have B divided by 2 times 4, which is 8. Therefore, that's going to be B divided by 8 into, we are going to remain with d squared minus d squared plus y is 0. So we are going to have bd squared divided by 2 times 4, which is 8. So we have bd squared divided by 8. And therefore, ladies and gentlemen, that is how we get the value of maximum shear stress at the neutral axis of this I-beam section. That is the formula of calculating the maximum shear stress at the neutral axis of an I-beam section. Now, considering these two equations, we have shear stress is equals S over 2I into d squared over 4, d squared over 4, and this second equation that we have already derived. At the junction of the top of web is at this point here, and bottom of flange the same point. So this is the junction between the top of web and bottom of the flange. So at this junction here, the value of y is d over 2. Using this equation 2, substituting y is equals d over 2 here, we are going to have shear stress is equal to S over IB into B over 8 into d squared minus d squared plus B over 2 into d squared over 4 minus d over 2, that is y. Therefore, when you square d over 2, you are going to have d squared divided by 4. And that will make this part to be equal to 0. And therefore, that is going to give us shear stress will now be S over IB into B over 8 into D squared minus D squared. So when we rearrange this equation, we are going to have shear stress being equal to S divided by 8I times B over B into D squared minus D squared. So when we rearrange the equation, that is what we are going to have. Equation 1, we have shear stress being equal to, we can factor out 4, so that we have 4 times 2, that is 8. So that's S divided by 8I into D squared minus D squared. Now, from these two equations, equation 2 as well as equation 1, we can see that there is an abrupt change in shear stress. Now, plotting the shear stress distribution diagram or the variation in shear stress for this I-beam section, we are going to have a shear stress diagram that looks like this. So we have a straight line from top to bottom, and then we have this, that is the neutral axis. This is the junction between the bottom of the flange and the top of the web. So going all the way up to that point, the same case down here. Now, when we derived the equation, we found that the shear stress at the top edge of the flange is 0. The shear stress at the junction between the bottom of the flange and the top of the beam is given or will be given by the first equation. And then we are going to have an abrupt change in shear stress. The same case to the lower flange. We have 0 shear stress at the bottom of the lower flange, and then the shear stress increases up to that, and then it changes abruptly, and then we have a curve that looks like that. Yep. Therefore, at this point, the shear stress will be given by equation 1, which is S over 8I into D squared minus D squared, which changes abruptly to shear stress given by equation 2, that equation. So the shear stress here will be given by first equation. The shear stress at this second point will be given by the second equation. At the neutral axis, shear stress is maximum. Therefore, ladies and gentlemen, that is how we plot the shear stress diagram for an I-beam section. Thank you for watching our video. Please consider to subscribe, and don't forget to hit the notification bell so that whenever we upload a new video, you'll be the first person to be notified. Thank you very, very much.